Hi, this is my video number 8. So in this video I'll talk on the autonomous system, and in this video I'll talk on I'll give you example on the how to determine the stability of the critical points. In the previous video, I have defined what we mean by the critical point is stable, or asymptotically stable, or unstable. So I would like to summarize those things, so that we say this isolated critical point C0 X0 is stable. This critical point for the autonomous system is stable if given any epsilon positive. We can find delta positive such that we have three conditions. First thing is that the trajectory, the trajectory C, let's say xt, yt, this is defined in the it's not clear. All right, so x0 y0 is stable if given any epsilon positive. We can find delta such that we have the trajectory, let's say that's our trajectory, is defined in the delta neighborhood, in the delta neighborhood. Neighborhood of x0 y0. So what we mean here is that the trajectory is defined, so we don't have a kind of divide by zero or something. So for example, if you have x0 y0 there, this is the delta neighborhood. So inside there we have the trajectory, where this trajectory is defined. So we don't have kind of 1 over x0 or something when x 0. So this 1 over x0 when x is 0, then this is undefined. So we don't have this thing. So this function is defined. And the second condition is that our trajectory c x xt yt is remain in the epsilon neighborhood. Epsilon neighborhood of x0 y0. And so remain in the neighborhood means we have this is our point, critical point x0 y0. If this is the delta neighborhood, then we have epsilon neighborhood here, and then our trajectories remain inside there. Remain inside there. You won't go out of that delta neighborhood, epsilon neighborhood. And the third condition is that if we take a limit, limit x approaches, t goes to infinity of xt, this is equal to x0, and limit y as t goes to infinity for y, that gives you y0. So in this case, if we have a condition 1 satisfied, condition 2 satisfied, and add another condition which is condition 3 satisfied, then in this case we say the x0 y0 is asymptotically stable. Okay, stable just if only two conditions satisfied, plus another condition here, then we call it as a asymptotically stable. And then we say the point is unstable. Yeah, the critical point is unstable. Critical point x naught, y naught is unstable if it is defined. It's defined in the epsilon delta neighborhood, yeah, but they remain outside the epsilon neighborhood. So that's the difference between the stable and unstable critical points. Yeah, for the unstable critical point, we have the trajectory. Our trajectory is defined, but they remain outside of the epsilon neighborhood. Yeah. Means that, for t as t goes to infinity. So it means that we have a let's say this is our critical points. So we have let's say this is epsilon neighborhood. All right. So our trajectory is just look like that. It goes out as t goes to infinity. So it's remain there. It's not coming back into the epsilon neighborhood. Now let me give you some examples to describe the stability of the critical point. Just a very simple example, because later on we go to more complicated case. Let's consider this three example. Let's say example okay. Let's say I consider first example. We have x dot equal to y and y dot equal to minus x. Okay. Second example, we have x dot equal to minus x, y dot equal to minus y. And a third example, I consider x dot equal to x and y dot equal to y. So it is not difficult to see that this the solution for that system, the solution for that system is given by, so we have x, y is r cos t, and x is r sin t. So you can see from there, if you differentiate that with respect to t, we have negative r negative sin t, so that gives you negative x. If we differentiate those things, that gives you cos t, that gives you y. Okay. Whereas for the second and third, for this problem, the solution we can have like x equal to x naught. We have negative x, so here negative t, e to the negative t. And for y, we have y naught e to negative t, where x naught, y naught any constant. Whereas for the third example or third problem here, the solution is given as x equal to x naught e to t and y equal to y naught e to t. If you differentiate, there you got the same thing. Now, for the first example here, so we can see that the solution for for part A, so we can see that if I squared both x and y and add them together, so what we have is x squared plus y squared is equal to r squared. So what you can see here, this is the circle of radius r squared. So we have a circle of radius r squared. That. So this is the trajectory of the solution. So we can see here this x squared plus x squared and the solution itself. Look at the solution. The solution is defined. Look at the condition given beforehand. Yeah, this is the definition of stable. We have our trajectory is defined in the delta neighborhood, remain in the epsilon neighborhood, and we have the other condition here. Now in this case, yeah, this is defined x r equal cos t. So whenever when you move t, so it still gives you a defined function or defined solution, and remain inside the delta neighborhood. So you can see here, it won't go out or it go inside. You know, just stay in that circle. And as well as if you consider, if you have, remember that we have the theorem, if xt yt a solution to our system, I use our system here. This is the autonomous system, and our system refer to the first example here. All right, and then xt plus alpha is also the solution. yt plus alpha is also a solution. So given that in mind, so we consider our solution up there, the first case. So we have x is for x plus t plus alpha, we have r sine t plus alpha, and y equal to r cos t plus alpha. Okay, if you look at this two solution here, square that, we still have x squared plus y squared plus equal to r squared. Still give you a circle. So which means that in this case you have infinitely many solutions. Yeah, infinitely many solutions. Why is infinitely many? Because you can change alpha. Each time you change alpha, you got different solution. Each time you change alpha, you got different solution. So basically you have infinitely many solution. But this infinite many solution turned out to be just, we have one trajectory. Okay, just one trajectory. So which means this critical point 0, 0 is stable. Okay. You might want to ask where is the epsilon, where is the delta. So of course in this case we can consider delta is equal to epsilon, and we can take any r which is less than that. Yeah, you can consider this, so that our trajectory remain in the delta neighborhood. Okay. All right. So what about the asymptotically stable, the third condition? Okay, we check for the third condition. For the third condition, we need to check the limit xt t tend to infinity. This equal to x naught. Our x naught is 0. Can we get that? Limit our xt is r sin t as t goes to infinity. So you can see here this sin t sometimes 0, sometimes different than 0, and so otherwise I would say it's not all goes to 0, because sine you have a what we say like that, a periodic function. So in this case 0 0 is not asymptotically stable, but it is stable. Stable but not asymptotically stable. So not asymptotically stable. Okay. So then what about others? You can check others. For the second case, okay, for the second case, of course, for the second case and as well as third case as well, this is well defined, which is satisfy the first condition, and you can see this. Let me write this. We have solution is given as x equal to x naught e minus t, y equal to y naught e minus t. All right. Of course, you can write this, or you can write this either one, either this or that, as a for this you can write e minus t as x over x naught. Okay, if you substitute into that, so what you have, substitute into that, we have y is equal to, so we have y naught over x naught times x. So what can you see? This is just a straight line. A straight line with difference depend on x naught and y naught. Okay, so in this case we have the trajectory is given like this is, let's say this is our critical point. The trajectory is look like that. So it goes inside because we have negative here. Yeah, it goes inside because we have negative, so it goes inside. So in this case, you can see that the trajectory remain inside the epsilon neighborhood. Now, because it goes inside, it will not go outside. Because you look at the arrow, it goes in. The direction of the arrow is toward the critical points. So for this case, it's stable. Yeah, so we have defined, and it's remain inside the epsilon neighborhood. Remain inside the epsilon neighborhood. Epsilon neighborhood is a long thing to write. That's considered neighborhood. Epsilon. You might ask where is the epsilon neighborhood? You just pick up any epsilon. Then you can see those trajectory still inside the epsilon neighborhood. Okay. Then if you take the limit for that, so you can see this. In this case, it is a asymptotically stable. You take a limit for the third condition. We have take a limit xt xt, t tend to infinity. This is limit of x naught e to minus t tend to infinity. So that gives you x naught. As well as y, t tend to infinity, yt limit t tend to infinity, y naught e minus t, that gives you y naught. So we take a limit, so it's tend to our critical points. So in this case we say the x naught y naught, the critical point for problem B is asymptotically stable. Okay. What about the third example? The third example, or C, we have the solution is I wrote somewhere. We have x equal to x naught e t, y equal to y naught e t. Of course, you can still write that et as x over x naught. You substitute into there, you got y is equal to y naught over x naught x. Again, this is a straight line. Okay, a straight line. Just like y equal to mx plus c, where c or c is 0 in this case. Okay, so in this case, this solution, this is defined. This is defined. It's remain in the So if you look at that solution, you can see that this is a straight line. So we have still like that. Oh, sorry, this should go through that. You know, that should go through that like that. So, but if you take the t getting bigger and bigger, what can you see? It goes towards the infinity, right? So you can see those x equal to x naught e t, that goes to infinity as t goes to infinity, as well as y naught et also goes to infinity as t goes to infinity. So which means the trajectory points outward. So which means no matter how small or how big you choose the epsilon neighborhood or delta neighborhood or epsilon neighborhood, no matter how big you choose the epsilon neighborhood, so those trajectories still point out. So it means this neighborhood remain outside the epsilon neighborhood. So therefore, in this case, those x naught y naught are unstable critical point. The critical point are unstable. Is stable. S naught y naught is unstable critical point, or the critical point S naught y naught is unstable. So now I with these three examples, I have a stable, we have asymptotically stable case, we also have the unstable case. So I complete these parts. For the next video, I'll talk on the linear system with constant coefficient, where we still deal with linear system. Now what we have is x dot equal to x, just a function of x. Say x dot equal to p of xy, y dot equal to q xy, and in that particular example, we just consider x equal to like x, y equal to y. So Now in next we consider where first equation we have xy, second equation we have xy, where you can write in terms of matrix and so on and so forth. Okay, so I think that's all for this video. Thank you.